Hi everyone, hope you're doing well. I'm Reza, founder of the optimizationcity.com. In this video, we answer this question: what is sensitivity analysis? Let's move on.
When we analyze the sensitivity of the number on the right-hand side, our goal is to determine how much we can change them while keeping the final table feasible. Feasible remain that none of the right-hand side number become negative. To help explain this case, let's consider the following example in more detail. Let's consider an example where we need to produce two products represented by x1 and x2. To produce this product, we use the four resources A, B, C, and D. The available amount of the resource are A equal to 6, B equal to 8, 1 equal to 1, and D equal to 2. The constraints of the problem are defined based on a limitation of these four resources. Additionally, if the profit per unit of the first product is 3 and the product per unit of second product is 2, the model can be summarized here. So we have two decision variable and four constraint. The optimal solution of the problem, which is determined by point C, which is here. This is the point C. We have x1, x2, and 4 slack variable. In the optimal solution, we observe that the resource 1 and 2 are fully utilized, while their level of resource C 3 and 4 are 3 and 2 third, respectively. This example show us the following question. So what is the difference between constraint 1, 2, 3, 4? So we'll discuss in this slide. How flexible are resource amounts, number of on right hand side to decrease or increase? Once you have found the best solution, we can explore the potential change to further optimize it. Especially if we focus on two types of analysis. First, how much can we increase the resource to enhance objective function optimal value? Second, how much can we decrease the resource without altering the current optimal solution? As the resource level are represented by number of right-hand side of the constraint, this analysis is known as a sensitive analysis of right-hand side. In the given problem, only constraint 1 and 2, which correspond to a resource A and B, are significant. Common sense tells us that if a constraint is important, it means the limited resource because all valuable resources are fully utilized. It causes S1 and S2 is equal to 0. Conversely, a constraint represents as an abundant where F3 is not equal to 0 and S4 is not equal to 0, which call this constraint as the abundant constraint. Therefore, our interest lies in determining how much we can increase scarce resource to enhance objective function value. Similarly, we want to find how much we can reduce non-scarce resource without impacting the optimal solution. Let's see this figure. Constraint 1 and 2 indicate a limited resource. Let's focus on the resource A. As we increase the amount of resource A, constraint A, which is line CD, shift upward in the parallel manner, causing triangular CDK to shrink. Here, the side CK and DK of the triangular DKC correspond to the constraint 2 and 4. As we continue to increase the resource A, we reach point K here, where the constraint 2 and 4 become significant. At this point, the optimal solution is located, and the feasible region is presented as the area A, B, K, E, F. When we further increase the capacity of the first constraint moves upward and maintain the parallel relationship to itself. However, this increase has no impact on the feasible region or improve the objective function beyond that point k. This is because the first constraint become redundant and the value of the first constraint will keep increasing till point k. The first constraint will intersect point k if right-hand side number is greater than 6. To calculate this increase, we simply substitute the coordinate of point k into the first constraint. In this way, the maximum increase in the first limit is from 6 to 7, which is equal to 1 unit. Okay, the diagram below illustrates the impact of the increasing of second constraint. Independent of any change of the first constraint is very important. As we increase the second constraint, we can improve the objective functions until the second constraint intersects point J. Here, this is point J. The coordinates of point J are determined by intersecting the second constraint here and the non-negative constraint of the variable x2, which is x1 is equal to 6 and x2 is equal to 0 as shown here. By substituting the coordinate of point J into the second constraint, we can calculate the new value of the right-hand side number in the second constraint and updated value of the resource B. So this is here we can see that the resource B can be maximal can be B is equal to 12. As a result, we can increase the right-hand side of the second constraint from 8 to 12, which is amount of potential increase of 4 units. Let's now examine the decrease in the right-hand side number of the redundant constraints. Because F3 and S4 are non-zero, the constraint 3 and 4 are considered as a redundant. Let's focus on the constraint 4 first. The diagram below illustrates that the first constraint, line ED, can be reduced till it crosses point 3 without impacting the optimal solution. Point 3 corresponded to x1 is equal to 3.3 and x2 is equal to 1.3. Therefore, the right-hand side number of the first constraint can be decreased to a maximum of 1.3 without altering the optimal solution. Now consider the third constraint. Again, similarly, we can decrease the right-hand side of this constraint such that the equation here minus x1 plus x2, which is equal to 1, which is third constraint, pass through the point 3. So the right-hand side of the third constraint become here. You just need to point C here in this equation. What is point C? Point C is here. Is let me see, is 3.3 and x2 is 1.3. This is the coordinate of point C. So therefore, the right-hand side of the third constraint become minus 2 by doing this calculation. This modification has no impact on the current optimal solution, which is point C. The findings from the preceding discussion for 4 constraints are summarized in the table here. As you can see that we have 2 constraints as a scarce variable, as a scarce constraint, and we have 2 constraints as a redundant constraint. You have the maximum change in the Z value and the maximum change in the right-hand side value in this resource. Considering the financial constraints that are commonly encountered in the economic aspect, we would like to determine the importance of the capital allocation among the different resources. Our main objective is to maximize profits, so we are interested in identifying the resource that can contribute the most profit growth. This information represented in the table below. So if yi represent the value of each unit of resource I, we can calculate yi using the following formula. So you can see that the resource 1, 2, 3, 4, resource 1 and 2 are the square constraint, and resource 3 and 4 are the redundant, and y1 and y2 is positive, and y3 and y4 is 0. We will discuss in the future that y1 and y2 is a shadow price of the first and second constraint. Thank you so much for watching me. If you are any question and need any assistance, please do not hesitate to contact us by email or by form by filling the contact form in our website, which is www.optimizationcity.com. Thank you so much and goodbye for now.